Alright guys, we have another related rates problem here. So let's just get to it. The top of a 5-foot ladder is leaning on a wall at a point 4 feet off the ground. It begins to fall at a rate of 1 foot per second. How fast is the base of the ladder moving away from the wall? So I'm just going to draw a general picture of what's happening here. So we have a ladder that's leaning on a wall. So it looks like this. Here's a 5-foot ladder. 5-foot ladder. And it's 4 feet. Boom. It's 4 feet off the ground. And the question is, they're telling us that it's moving at a rate of 1 foot per second. So it's falling vertically down by 1 foot per second. So it's going downward. And they want to know how fast is the base of the ladder, this guy right here, moving outward that way. So before we do anything, I think the first thing we should figure out is, well, the length of this side of this triangle. Clearly, this ladder leaning on the wall, touching the floor, it makes a triangle. We should probably figure out how much this side of the length of this side of the triangle is. So of course we have a right triangle here. So let's use the Pythagorean theorem, which is x squared plus y squared equals c squared. A squared plus b squared equals c squared, right? Okay. So we have x squared plus y. I'll say this is y, is 4 squared equals 5 squared. So if you do this, you'll figure out that we have a 3, 4, 5 triangle. So x here is 3. All right, so this is what we're looking at now. We have a ladder, a 5-foot ladder, that's leaning on a wall, and the height to the top of the ladder is 4 feet, and from the wall to the base of the ladder is 3 feet. And they're telling us that it's slowly moving down the wall at 1 foot per second. How fast is it moving this way? Okay, so here's what you have to realize, that this y component and this x component here, they both change, like the length of the y component and the x component, they both change with time. So they're actually functions of time. So what I'm going to draw right here is a little graph of each of these. So here's y as a function of time. And I'll draw something like this. Boom. And here's x as a function of time. Boom. Boom. And here is the length of the ladder as a function of time as well. Okay. Maybe I'll zoom out. T, T, T. So how high is the ladder off the floor? We're talking about the y component right now. How high does it start off of the floor? Well, it starts off at 4 feet high. And as time passes, we realize that as each second passes, it gets 1 foot lower and lower and lower. So it's going to look like this. That means as 1 second passes, it's going to have a value of 3. As 2 seconds pass, it's going to have a value of 2, and so on and so forth. So that means it will take 4 seconds for this guy to have 0 distance to the floor. Okay, so how can we write this guy as a formula? Well, his y-intercept, so y of t, equals, this is clearly a line, and its slope here is decreasing by 1, and its y-intercept is 4. So in a way, they've told us that dy dt is equal to -1, right? Because the derivative of this function is the slope. It's the slope of this line, which is -1. And it was also given in the question. So you have to really analyze what's happening because they're giving you a lot of clues. You just have to make sure you read it the correct way. All right, so let's look at our other guy, x of t. So x of t, where does he start? He starts at 3, right? And guess what? As the ladder moves away from the wall, the length increases by a certain rate. So he goes something like this, his graph. And it's definitely a line. So we have x of t equals well, the y-intercept is 3, and we have t times the slope of the function. But the slope of the function is dx dt, right? We just said that right here. The slope of this function is dx dt, just like how the slope of this guy right here was dy dt. Okay, and lastly, let's do the last. So c of t is the length of the ladder as time passes. Guess what? As time passes, the length of the ladder itself does not change. So it's always going to be 5 feet. So it's a constant function. So dc dt is the slope of this line right here, of this function. And we can all see that it's 0. And I think we have enough information where we can start attacking this problem right now. So we have 3 different functions that are all functions of time, and they're all related by this equation right here. X squared plus y squared equals c squared. But of course, this is just like an abbreviated name. How we're going to actually write these guys is like this. X of t. You could put a parentheses. I like using brackets. Plus y of t bracket equals c of t squared. All right, so I've taken this guy and I've rewritten them in using their full name. No abbreviations, all right? I show that they're all functions of time. Okay, so our goal here is to figure out how fast is the base moving away from the wall. And how fast the base is moving away from the wall is this guy right here, dx dt. So we wanted dx dt to pop up somewhere in our equation. So let's start by just taking the derivative of this whole thing. Okay, so let's take d dt of this side and then d dt of this side. Boom, boom. So what do we get? We already said that, actually, no. We'll be a little bit more thorough, okay? So the thing about this one is we have implicit differentiation and we got chain rule all around. So let's start with the left-hand side. What I'm going to do here is I'm going to drop the exponent, multiply it by the inside function, right? We're doing a chain rule right now. And I take 1 away from the exponent. Then I'm going to multiply this by the derivative of the inside function, which is dc dt. I took the derivative of the inside function. But we know that dc dt is 0 because this is a constant function. So this whole side eventually goes to 0. Okay, good. Next, we're going to have to split these guys up. So we have d dt of this guy and d dt of this guy right here. So x of t squared and y of t squared. And again, we have to use the chain rule. So the chain rule here is we drop the exponent times the inside function, take 1 away from the exponent, we're just left with 1, times the derivative of the inside of the function. The derivative of x of t is dx dt, right? It's the slope of this line. And then we're going to do it again for this guy. Drop this guy, drop the exponent, keep the inside function the same, and then multiply it by the derivative of the inside function. So the derivative of y was dy dt. Okay, so let's go ahead and let's start plugging in things that we know. So they told us that dy dt is -1. So we can definitely fill that guy in, -1. And we can pick any point from this graph, and we can pick any point on this graph for x and y. Just make sure their times are matching up. So if I pick when t equals 4 here, I gotta use the point for Jesus Christ. When I pick time equals 4 there, I gotta do time equals 4 also for my x part, my x graph right here. I don't know what's going on with this guy. Come back, I need you. All right. But we're gonna pick the easiest one, which is at time 0, right? At time 0, we know that y is equal to 4, and we know that at time 0, x is equal to 3. So 2 dx dt plus 2 equals 0. So what do I get here? I get 6 dx dt minus 8 equals 0. All we got to do is use some simple algebra, and we see that dx dt equals 4 over 3. So this is the rate at which the base of the ladder is moving away from the wall. So I hope that made sense. We're going to do 2 more examples of these. Like I said, the key to these problems are just figuring out, understanding what dy dt means, what dx dt means, and dc dt means. You have to think about it like graphically, and it will make sense to you. If you just try to go in algebraically, you're going to get confused and you're going to get lost in all the shenanigans. So really try to graph everything out and try to get a good understanding. All right, guys, we'll have 2 more videos on these.